5.2, approximating areas under curves. This is going to be video 1, and I want to start with this concept of a car going at a constant velocity. We could actually draw that. We could graph it, and remember, time is always on our independent axis, and then we would have our speed, or time, miles, distance, not speed there. And so I would say if a car was going, let's say 60 miles per hour and in a constant velocity, so it's a straight horizontal line, what would happen? We could figure out what was happening when it was going 1 hour, and what if we wanted to know when it was going 2 hours? So we could say we would know how far it went, or a displacement of would be the area under the curve. We would know that it would go 60 miles the first hour and another 60 miles the second hour, or we would know that it would go 2 times 60 for 120 miles. So 2 hours times 60 miles per hour gives us 120 miles. We call this area under the curve displacement. I'm not going to get it all on there. We could talk about it being length times width. It was 2 on this and 60 for length and width, and then we just multiply the two together. So it is on an interval that's closed from 0 to 2, and all of these concepts that we've just used to apply this area under the graph or the curve, in this case it was a straight line, we could just length times width. That was easy. Area that way was easy. But what if it is a curve? I keep saying curve. So for this case here, it's saying this velocity is t squared times squared. How do I find the area under this? We're going to use rectangles, and they don't have to be the same. They could have been all different sizes. So for example, in this first picture, I could have done rectangles like this. Oops, that's not a rectangle. Rectangle like that, a rectangle like this, maybe thinner ones, but they're not regular. But the easiest way to calculate would be with regular partitions. So you can see here, in this first graph, we only used 2. And we could find easily the length times width, the area of a rectangle, and we could calculate with 2 of them using this function, plugging into this function v equals t squared, using these points to get the height. And we can count literally from the graph our width. So we could do that easily. And then you can see we get an area approximately 160 units squared. And then this middle graph, we used looks approximately 8, and we see approximately the area, 8 rectangles, an area of 170. But this last one, we're going to say n is the number of rectangles, and this one has 64 rectangles under this curve. Now notice each of these in these pictures, we have a piece that's over, and then we have a gap that's open under. So we have to take into account, we want to make sure those could be as small as possible. These two on this middle graph are definitely smaller than the 2 under and overs on the first graph. This last graph, they're the smallest. They're harder to see, but they're still there. There's still gaps. We're not perfectly following this curve, but it looks like to be the best. That the number of rectangles that we take, or in regular partitions, seems to be a better approximation of what the area under this curve is. Notice the area approximately is 170.625. So in this case, maybe that's closest to what we would expect to be the actual area. So we have here as our definition regular partitions. And in order to find this, and we're saying it's delta x, how is our x values changing along the x-axis for each partition? In order to find this, I'm going to move this up. We're going to go ahead and say that delta x, and it's written here, is on the interval endpoints. We're going to start with b minus a divided by the number of intervals we want to find. So it has in there all the correct sub-notations that we could use. Subintervals are called the grid points, and they create regular partitions on this interval. The kth grid point is, and it has this formula here, and I want to explain it real quick. If I'm starting at A, I'm basically saying, well, I want to take the next plus 1 delta x over. And then if I want to do the next one, well, this point would be a plus 2 delta x over. And then the next point would be a plus 3 delta x over, whatever delta x ended up being. But I'm always starting from that beginning endpoint, and I want to count consecutive integers as I go along, as I'm counting till the last one, n. So that's why we say x sub k is equal to a plus k times the delta x, where k is integers, and 0, if we had plugged in 0, would be a. So it would be from the starting point and every consecutive even regular partition over from the beginning of our interval. So from there, I have the widths of these rectangles, and honestly, I'm going to try to find formulas to evaluate easily the areas of these rectangles under a curve. So I've got widths. I need to figure out heights. So we're going to use Riemann sums, and it like jumps into a whole lot of information real quick, but I still need to talk about heights. So in order to talk about the heights, because we were going to go to our function for a height, so from here at this point, this would be my height, and it happens to be whatever value I want to plug in, whatever subinterval point it is, I want to plug into the function, and I'll get the height of that rectangle. So for this particular rectangle, it's the point that's on the graph, so we'll say f of k sub x, and the book uses also an asterisk star in our notation. So we have that this then is the height, but as we move along the function, that height is different for the next interval. It's not the same height. So for this next one, this is the height, and it's not the same. So it'd have to be the next x value that we plugged into the function. But then notice I have this dotted line. It's the midpoint of the rectangle that I have touching the function. So there's 3 different ways, and a German mathematician, Riemann, said, hey, wait, we could do this. We can use left corners of the rectangles, the midpoints on the top width of the rectangle, and right corners of the rectangles. So there's 3 different ways we can calculate for this. And if you notice, we have a lot of different notations, but here is one area for the first rectangle. It's the height times the width, plus the height times the width of the next rectangle, plus, and we keep going until the last rectangle. We're going to keep adding these and summing them up to total the area under the curve. So we can have, I'm going to draw quick pictures of the different left, right, and midpoint. So if I have a curve like this, left would be the left corner of my rectangle. If I want to do the right corner, oops, not quite level there, my right corner of the upper side of the rectangle, upper width. And then the midpoint would be like the ones I had already drawn, where the midpoint between A and x sub 1 is halfway, and that's the part of the rectangle that is touching. Notice definitely, and here I'm definitely going to say that, okay, wait a minute. Let's look at this. If I'm going to have a bunch of these rectangles for the left, I see that I have nothing over the graph, the function. I only have areas open that I did not count for under. So this would be an underestimation. In the right endpoints, if I was to draw all the other rectangles the same way, I would see I have nothing under the rectangle that's open, and I'm counting area above the function. So this one's going to be an overestimation. And if I look at the midpoint one, remember we're going to be trying to do midpoints, so I'm going to have a combination of both over and under. So this one, it's maybe the best currently of our approximations, that I'm hoping that they kind of equal or balance each other out, or justify back and forth taking an average maybe of over and under, and maybe the midpoint ones are the best options for finding area under a curve. Remember though my pictures do not show it, they're to be uniform rectangles. So let's go ahead and we're going to show you a couple of things here where it says sums of positive integers. Oh, I'm sorry, went ahead too fast. Let's go and do some examples. I want to go ahead and I want to do a couple of examples that seem a lot of work, but to start with and understand the concept best, I believe that's the best way to do it, and then we could do things on the calculator. So for number 9, we're given function 3t squared plus 1. So the velocity, and when the time is between 0 and 4, it could be seconds. So basically, we're on this interval like this. I just wanted to write it both ways. The problem wants us, it says in the book, to find displacement. It says the velocity in feet per second of an object moving along a line is given by this equation on this interval. It says divide the interval into n equals 4 sub-intervals. So we're going to use from 0 to 1, 1 to 2, 2 to 3, 3 to 4. On each sub-interval, assume the object moves at a constant velocity equal to v evaluated at the midpoint of the sub-interval, and use these approximations to estimate the displacement of the object on the entire interval from 0 to 4. So we're going to go ahead and I'm going to draw a picture. The book actually has a picture of but I'm going to draw it by hand here. So let's pretend this is our function, and I'm going to go ahead and say 1, 2, 3, and 4. And we want to go ahead and start with 4 intervals. They said n equals 4. And we're going from 0 to 4. So I could do one rectangle here. Oops. One rectangle. I'm going to, do it this way. And I ran out of function here. But they said midpoints. So back to the midpoints. That means at 0.5, at 1.5, at 2.5, at 3.5. This is the part of the rectangle that I want touching the function. Oop, drew it too high, sorry. Okay. So this is a very rough sketch of what my rectangles should look like. And notice then, remember the formula for what x value is. We said it changed then. for this midpoint. It should have been if it was going to be a width of 1, and if that was the case, we would be using left endpoints or left corners. We would be using this formula. But this is midpoints, and notice it was a little easier to figure out at this point from drawing. We're going to come back more into why and have that little shortcut that was the slide I accidentally showed you. But from here, I need to go ahead and say my delta x is what? All right, let's figure that out algebraically. So my delta x is going to be the b minus the a over the number of intervals, n, which is 4. And I see that my delta x is 1. So then I'm going to use these midpoints for all the heights. So then my area should be approximately 1 times, and I'm going to plug 0.5 into the function. And that would be the first rectangle. And then I'm going to add it to the area of the second rectangle, which is a width of 1, and the height is going to be 1.5 plugged into the function. And then I can see plus the next rectangle has a width of 1, and we're going to plug in that height of 2.5 in order to find the height into the function. We're going to plug in the x value. And then I have to have one more. So if I have 4 subintervals, I now have 1, 2, 3. I need 4. So it's one more rectangle, 1 for the width, times the height will be 3 times 3.5 squared plus 1. So plugging 3.5 into the function. All right, so I am now going to sum up all these areas of the rectangle. Oops. The reason I added that, and I just realized I shouldn't have, because the widths are regular partitions and all the same, I have a 1 times, 1, the next one times 1, the next one times 1. I can factor that out. And to make life easier, I could have rewritten my width in front and then all my heights being summed up inside. So I could have written it like that. And in the future, that's what I will be doing. It will always have the width being just multiplied out front and summing the heights. So from here, though, if you go ahead and do all the calculations, I get approximately, it should be 1 times the sum of 1.75 plus 7.75 plus 19.75 plus 37.75. And when I go ahead and calculate that, I get approximately 67 feet. So that is going to be the displacement of this velocity. So that is what I'm talking about as far as what's under the area under the curve. But it's not feet squared because I'm talking about velocity. So that is the first example using the midpoint. Second one. You could do it with more, but we're going to move on to one like in homework would be number 13. We want to know this displacement for this velocity, and we want to use left endpoints. So first thing I'm going to do is find my delta x, or my widths. I'm going to do b minus a divided by the number of intervals, and I see 2. If I was not to graph the function itself, let's just try to figure out what values I want to use. So you can always use in this one that a plus the k delta x, that works. Or you can look at it visually. I should have 1, 2, 3, 4, 5, 6, oops, not enough, 7, 8. This is the interval, and it said, though, width of 2, using the left. So I'm going to start from the left endpoint of 0, having a width of 2, having a width of 2. So it would be a plus 1 width, a plus 2 widths, a plus 3 widths. Okay, I need 1, 2, 3, 4 intervals, right? So I have 1, 2, whoops, I missed something. All right, sorry, I made that wrong. So I have my 4 dots that are going to be the values I'm going to use for the 4 intervals. I'm going to use 0, 2, 4, and 6. If you want, you can plug and chug in that separately and then add up. But if I know the width is 2, it's going to be, so I'm pulling out as a GCF all the areas, 2, and then I'm just going to go ahead and calculate, plugging 0 into this function, I get 1 for the first one. And then if I plug in 2 for t, plugging it in, I should get 1/5. Plugging 4 in, I should get 1/9. And plugging 6 in, I should get 1/13. And then I make sure I have to sum those up and multiply by 2 at the end here. I should get approximately, now the book's answer is 2.76, and I kept coming up with 2.78 meters. So you can be slightly off depending on how you want to round. So we're going to go ahead, and I want to go and do number 21 as our last one. So for number 21, I have cosine x, and I'm going to be on this interval from 0 to pi over 2, and I want to do sub intervals of n equals 4. And we're going to do left endpoints and right endpoints, so corners of our rectangles. So if we do A, we're going to do left first. If I draw this, this is what my curve looks like for cosine from 0 to pi over 2. And it says they want 4 subintervals. So I'm definitely going to have to split it. And how do I find the delta x? Remember, it's going to be b minus a divided by the number of intervals. So now I have that the width is going to be pi over 8. So this one, first one should be pi over 8. So this one should be pi over 4, and this one should be 3 pi over 8. If I'm going to go and do the left intervals, I'm going to use 0, pi over 8, pi over 4, pi over 3, or 3 pi over 8 for my values to plug in for heights. And then for B, when we have to do the right, we're going to use pi over 8, pi over 4, 3 pi over 8, and pi over 2 for my right intervals. So that's what we're going to use to calculate from there. So if you want, remember, you can do the same process that we were just doing and give me a decimal approximation. I would go 3 places in the decimal approximations. You should end up, for A, approximately an area of 1.185. And for B, you should get an area approximately, where did it go? 0.791. So look, if we can see, there's a big discrepancy in area for left or right. So one of them is obviously going to be over, and one of them is going to obviously be under. So pay attention. You can't always assume right or left is going to be the over or under until you kind of get a feel of what the graph looks like. And let's go back and check, why is the B, the right approximation, so much smaller? So if I do the right, that means this is my rectangles for the right endpoints. And I can see with drawing the graphs and having the rights, that's definitely going to be my under approximation because there's nothing over the graph. And if I want to go ahead and try the rectangles for the left corner, we see we have this. And we're definitely going to be over. So if we were to do the midpoint one, that value should fall in between those two numbers and make a lot more sense in an area and finding a better approximation of the area.